Welcome to this instructional video to finish out Chapter 6. So in class we went through the mechanism of chymotrypsin, a digestive serine protease, a DSP. And then this image here is to remind us of the active site of this DSP, chymotrypsin, and we see the catalytic triad. What we need to do next is to think about what if there's a mutation among amino acids in this catalytic triad? How might it impact the activity of the enzyme? So these two that we're going to talk about right now are centered on serine 195. Let's review. What was the role of serine 195 in the mechanism of chymotrypsin, a digestive serine protease? Well, its main role was an active site nucleophile that actually attacked the carbonyl of a peptide bond. That was what the mechanism showed. That's what we went over in class. Now, serine 195 all by itself is a pretty bad nucleophile. In the acid form, it's a bad nucleophile. So histidine 57 deprotonated serine 195. It's now an alkoxide ion, which, as you know from organic, is a very strong nucleophile. All right. So, what if we replace serine 195 with alanine? What would be the effect on enzyme activity? Some of these I think are going to be obvious, some maybe not so much. Let's just use a numerical scale from 1 to 3, where 1 is diminished enzyme activity, maybe no change or diminished, to 3, and 3 means enzyme is dead. It's abolished. The enzyme activity has been abolished. Well, let's look at the mutation serine 195 alanine. And so what you have to do in these types of questions is look at the new amino acid side chain, or think about the new amino acid side chain, and ask the question, can this side chain play the same role as the original, the normal, or the wild type side chain played? And in this case, it's definitely no way, man. Look at this. It has to be a 3. This enzyme is dead, folks, if you put an alanine in for serine 195. Because we know alanine will never play the role of a nucleophile. No matter whether it will never play the role of an acid, a base, or a nucleophile. So this is just not going to happen. This is definitely a dead enzyme. All right, well, what's another possibility here? I'm just giving you 2 possibilities, but you can think of others, surely. What about serine 195 cysteine? Well, serine is OH, cysteine is SH. They're kind of cousins that way. What do you think this might impact the enzyme activity? Histidine 57 could deprotonate the hydrogen on the cysteine side chain, and what we would get is ultimately we would get cysteine S, like a thiolate ion. Wow. You are going to now get to use your organic chemistry knowledge. Why did you take organic chemistry for 2 years? Who really knows? But here you are. Okay? A thiolate ion, S minus, is actually more nucleophilic than OH. So I think this mutation is not that serious. I think I would predict a 1. For this reason, the thiol group of cysteine can play a similar role as the hydroxyl group of serine. And remember, technically this was an acid first because it has to be deprotonated to be a better nucleophile. So acid plus nucleophile. And in fact, there are some proteases, enzymes that catalyze the cleavage of the peptide bond that have cysteine in a position where serine is in chymotrypsin. They're called thiol proteases. So this mutation would probably not be that big of a deal. This would be a conservative mutation. The one up here, definitely radical. All right, I hope you know where we're going with this now. So let's keep playing this kind of game here. You know, what happens during a mutation. So in this one, we're going to talk about histidine 57, and we know histidine 57, a very important member of the catalytic triad of chymotrypsin. Its role was to play a general base, deprotonating serine 195 so it can be a better nucleophile. So if we say histidine 57 to alanine, then here we go again. Clearly this enzyme is dead. Okay, the side chain of alanine will never, hey, let's make that bold, or all caps, play the role of a base, which is the role histidine 57 is playing. So you want to kill this enzyme? Put an alanine in histidine 57. To be honest with you, ladies and gentlemen, there's probably nothing you could substitute for histidine 57 and have a functioning enzyme. To be honest with you, you might say you could put lysine or arginine there, but that doesn't make any sense, right? I mean, that doesn't make any sense because both of those are basic amino acids that would be in the acid form at pH 7. So again, remember in class we talked about this enzyme runs at pH equals 7. Also putting aspartic acid or glutamic acid in the active site. If I asked you about that, you know, your answer is, you could answer, I think, any of the numbers as long as you could justify your answer, right? If you put glutamic acid there, would it still deprotonate the serine? Well, it might do that. These are just thought experiments, right? So if I give you a mutation, and then you give me a number from 1 to 3, then your justification of that really is what I'm looking for on whether you understand how this actually works. Now, I said you can't really put anything there. I think that's just the case for this particular enzyme. I think it would be difficult to put anything other than histidine 57 in reality, not on paper, in reality, and this enzyme work. All right. Well, what about aspartic acid 102? Aspartic acid 102, very important member of the catalytic triad of digestive serine proteases. In one part of the mechanism, it played a structural role, helping hold histidine 57 in the proper orientation so it can act as a general base. In another part of the mechanism, we upgraded. We upgraded its role to catalytic because it stabilized some of the charge that develops in the transition state of this enzyme mechanism. So here we go. What if we change aspartic acid 102 to glutamic acid? Well, wow. What number are you going to choose here? I don't think 3 is where I would go with this. I mean, I think you could put a 1 or 2, and then your justification would kind of have to map back to the number that you chose. Here, I think you could go for 1 or 2 for this reason. So glue can play the same role as aspartic acid in position 102. And that is basically hydrogen bonding with histidine, stabilizing the transition state. Glutamic acid can do the exact same thing. They're both acidic amino acids with a fairly similar side chain pKa's. Now, if you put a 2 there, then you might could have an argument here that, well, glutamic acid is a little bit longer. It's got an extra methylene group, an extra CH2 group. There could be some alignment issues. So that's why you might choose to go for a 2 instead of 1. And as long as you can justify it, you can put a 2. But if you just put a 2 and you don't tell me why, then I don't know what you're thinking. Okay, so let me put this in here. So glue can play the same role as aspartic acid in position 102, although there may be, that's not one word, there may be some issues with proper alignment in the active site. And what I mean by that is they're not the same size. So is the fact that CH2 has an extra CH2 group, could it not interact with histidine quite as well? Maybe so. Will it not stabilize the transition state quite as much because it's not in the proper orientation or alignment in the active site? Possibly. Who really knows? This is a thought experiment. And again, 3 I don't think we could go for, but 1 or 2 as long as you justify your answer. Let's do one here on the fly. What about aspartic acid 102 asparagine? I'm not going to justify this, but I think we see where I'm not going to write a justification, but I think you see where we're going with this. Can asparagine play the same role as aspartic acid? Well, can it hydrogen bond to the histidine? Perhaps, but the main role of aspartic acid 102 and the second part of the mechanism was charge stabilization. Will asparagine ever be able to stabilize to charge the positive charge on histidine in that mechanism that we went over in class? I don't think so. So here I would probably lead toward 3, but probably a 2 or 3 would work here as long as you can give some justification. All right. So we play the mutation game to see if you really understand what's going on in this mechanism. Again, this last one was for aspartic acid 102. And let me go up here, and it basically played 2 roles. Let me just summarize this for the notes. 2 roles, structural and plus catalytic. And this catalytic was transition state stabilization. I know we could call this hashtag TSSVCN. That's why I'm pretty skeptical about asparagine replacing aspartic acid. It's just not going to stabilize the transition state like we need it. In fact, I think I'm going to change my answer. I think I'm going to go for a 3. I think that's a problem. Lack of TSSVCN. I think that's a problem. All right. Well, to kind of finish up here with chymotrypsin, you knew it had to come up. What about some type of pH profile? What is the pH profile of the enzyme chymotrypsin? Well, here we go. If you look at the curve, it's up here on the top right. And let me label this up for us because we need to have a good plot. So this is the rate of chymotrypsin activity versus pH up here on the top right. And so I need to make sure you know this is rate or velocity. I guess technically velocity, V is velocity, but it's just a rate. And it could be, I don't know, micromoles per second is a valid unit, so let's go with it. Of course, pH does not have a unit. Wow, what does this bell-shaped curve pH profile for chymotrypsin activity tell us? Well, it tells us, at least for this plot, there's two ionizable side chains involved in the mechanism, or at least allowing the enzyme to be active. All right, you know any pH profile is sigmoidal curve, but you can stitch two sigmoidal curves together and sometimes you get a bell-shaped curve like we have here for chymotrypsin. So there are two important ionizations in terms of enzyme activity. And how can you tell what the pKa of these ionizable groups that are so important? Well, it's the midpoint of the curves. So if we go here, then this one is right about 7. So something with pKa ballpark 7 is involved. And then as we go over here, midpoint of the curve, other curve going down, something has a pKa of about midpoint of 9. And so what I've done is I've taken this curve and I've split it in half just for discussing it. So let's just take the left part of the curve, below 8 and below, and I've just kind of cropped it so we can kind of see what's going on here. So what do you think? We went over the mechanism in class. You know the players of the game. What do you think has a pKa of about 7, and in its acid form, really this is what we're talking about. Let me just draw this line. This would be the acid form of this group. This would be the base form. So at pH's below its pKa, it's going to be in the acid form. And in the acid form, this group is not promoting enzyme activity. How do I know that? Look at the curve right here. We have very little activity left of this midpoint, and we have a lot of activity to the right of this midpoint. Okay? And I think my OCD is kicking in. I think I'm going to have to redraw this dotted line. Sorry. Man, that's a lot better. I like that. Okay. So, which ionizable group is it? Well, I think based on the mechanism we talked about, I think it's histidine 57. Come on, right? So over here, histidine 57 is going to have this structure. It will be in the acid form, and then it will not act as a base, not be able to act as a base. Ladies and gentlemen, we said that was the initiating event of the mechanism. If histidine 57 doesn't act as a base, oh look, we even have the copy up here, the mechanism up here. If histidine 57 doesn't act as a base, this enzyme is not going to work. And at pH is below 7, then not much activity according to our plot. So we know this is histidine 57 is responsible for this, and its pKa is right at 7 here. And we know in water it's 6, so the fact that it's 7 is not a big surprise to us. Now over here, and you may say, why does activity go up so much? Well, over here, hey, it's ready for prime time. Look at this. It's now in the base form. I don't like the way I do that. Let me try again. So, it is in the base form and able to deprotonate serine 195. That was a big part of this mechanism, a huge part of this mechanism. Oh, I guess we could even show that. Look at this. We can show at least part of it right there. This right here is a major part of the mechanism. Oh Lord, I can't help myself. Here we go. There's part of the peptide bond. And then, let me do this in red. I think that'd be much more dramatic. This is pretty much what we're seeing above, right? So it's also right here, up here on the mechanism up top. Okay, so this makes perfect sense. But if you do the work, if you do the experiment, you might think that this enzyme activity would just level off and it'd be a sigmoidal pH profile. Everything's right in the world. Histidine's not in the right ionization form. But that's not the way it goes. I mean, experiment has shown, and we are governed by experiments, that this has a bell-shaped curve. Somewhere past 8, the enzyme starts decreasing its activity. And according to the plot, there's some ionizable group involved that has a pKa of about 9. About 9. Now, you should stop this video and put your head around the question, what ionizable group could this be that has a pKa of about 9? Okay? If you look at side chain pKa's for the amino acids, there's really nothing around 9. Now, there's a cysteine about 8.3, but we haven't really invoked the cysteine in this yet. We haven't even talked about a cysteine being important. So I'm kind of skeptical of that. What else could it be? Well, if you look at your pKa tables, there is something about pH 9, a pKa of about 9, and that's an alpha amino group. And you may say, well, you haven't mentioned an alpha amino group either. And I would say, well, that's true. So the next part of the curve is something I'd have to give you some more information on if this was a test question. There's no way you would know how to answer or analyze the right part of this curve past pH 8 without me giving you more information. Okay? So what's going on? Well, here we go. We just saw the left part of this curve. Here we go. Over here, this was an issue with histidine 57, and then we got everything going up, and then it kind of levels off, but then it reaches a maximum activity at a particular pH. Let me just, for the sake of completeness, let me write in these units because units are important. Okay, and we said, hey, this was about something with a pKa of about 7, and then something with a pKa of about 9. So this is just kind of for the notes here. It's like, what has a pKa close to 9? Well, if you close to 9, that can impact the pH profile. Well, here we go. What we've got is, we've got some other ionizable side chains. up here. So what else could it be based on what we've already talked about? Well, in the past, people have just said, oh, I bet serine 195 has a perturbed pKa. So let's write that down. There, it's a bold statement. Serine 195 might have a perturbed pKa close to 9. Well, I guess that's possible, from 13 down to 9. You know, it's not completely unreasonable. But what is unreasonable is to say that deprotonation of serine 195 would cause the enzyme activity to decrease. That's kind of what you're saying, right? So if serine 195 had a pKa close to 9, then right in here, right in this area, we would start getting serine 195 O negative, right? Because we're titrating it, we're deprotonating it. Is formation of serine 195 in the base form, is that going to cause the mechanism to go down? The activity to go down pretty much close to 0? No, that would support the mechanism. That's what we were needing serine 195 to be negatively charged in the mechanism. So this can't be our culprit, if you will. Okay? We need this for the mechanism. So it can't be the other issue in this bell-shaped curve pH profile, because we need to form this. Let me see how to write this. This does not disrupt the mechanism. It supports it. So this cannot be the answer. This is not it. No. So basically, that can't be it. That would support the mechanism, not work against it, and make the activity go down. So that's not an answer. That's just not it. A lot of people just start throwing out side chains, and that's fine, but you've got to see, well, does deprotonation of the side chain, what we're looking for is something where we have deprotonation of a side chain or another ionizable group that would decrease activity. Again, I just said there's no way for you to know this based upon given information. This is one where I'd have to give you more information. Let's see if we can figure this out. So here we go. Here is chymotrypsin. Our DSP. And it turns out that chymotrypsin is a trimer. It has 3 subunits. Also, isoleucine 16 is the amino terminal amino acid of the B chain. So it has a free alpha amino group. So let's see if we can find this up here. Right here, here's the B chain. Look at this. This is isoleucine 16. Now I know what you may be saying. Why isn't that number 1? Well, because the numbering of the chain starts with the A chain. That's the number 1 amino acid. And so isoleucine is 16 because they're just keeping the numbering consistent as you go through the 3 different chains. Okay? So what's so special about isoleucine 16? Again, you would never know this unless I told you this. Okay? So here we go. Its alpha amino group forms an ionic interaction in the acid form that helps stabilize the active site of chymotrypsin. As a result, loss of this ionic interaction will cause the active site of chymotrypsin of our enzyme to be, let's just call it malformed. The structure has been disrupted. It's malformed. As a result, ladies and gentlemen, if the active site is disrupted, we're going to have lower activity. Does this part of the pH profile make sense now? Yes, its alpha amino group should have a pKa ballpark 9. That's what we have here. So below pH of 9, you're going to get the alpha NH3 plus form for isoleucine 16, and above 9 you're going to get alpha NH2. And with the alpha NH2 you get no ionic interactions. No ionic interaction. And this just goes down to what we said over here. So pKa if you get past 9, the enzyme activity goes way down, close to 0. It's a dead enzyme. Why? Because an alpha amino group, it's ionizable. Any ionizable group can show up in a pH profile. It forms the base form. You lose an ionic interaction. If you lose an ionic interaction between the alpha amino group of isoleucine 16 and some other ionic partner, I'm not being specific about that right now, the active site is malformed, and then the activity is going to start going down. Again, there's no way you would know this to be true unless I gave you some additional information. So the pH profile, the first part of the pH profile, you should have been able to predict histidine 57 was involved. The second part of this pH profile, past 8, I would have had to give you some more information. But this pH profile tells us one thing very clearly, is that digestive serine proteases need to be in the small intestine where the pH is about 7. Can DSPs cleave peptide bonds in the stomach? No. Why? Because in the stomach the pH is very low. In fact, it's not even on the scale here. pH of stomach close to what? Ballpark 2? Chymotrypsin is dead at pH 2 because histidine 57 will not be in the base form, which it has to be to get the mechanism started. All right, ladies and gentlemen, Chapter 6 is now complete. Thank you.